Assalamu alaikum everyone. My name is M.Sadman Aster. I have completed my Bachelor of Science in Electrical and Electronics Engineering from Islamic University of Technology. I have enrolled in Masters of Science in Electrical and Electronics Engineering from Islamic University of Technology. At present, I am serving as part-time lecturer at Daffodil International University. There I am teaching the courses of basic electronic devices and circuit and basic electronics courses for both theory and lab courses, and I am also serving as adjunct lecturer at Ahsanullah University of Science and Technology. Today the topic of discussion is semiconductor diode. So I will be explaining and discussing about semiconductor diode. We know that what is semiconductor. Semiconductors are of two types. One is intrinsic semiconductor, another is extrinsic semiconductor. Intrinsic semiconductors are the purest form of semiconductors. There are no impurities added on it. And extrinsic semiconductors are those types of semiconductors where impurities are added. The impurities can be of trivalent or pentavalent type. When we dope a semiconductor with trivalent materials like boron, aluminum, gallium, indium, those type of semiconductor becomes p-type semiconductor. Trivalent impurities are those type of impurities or materials who have 3 single valence electrons at the outermost shell, and whenever we dope a semiconductor material with a pentavalent material or pentavalent impurities, that type of semiconductor is called n-type semiconductor. And in case of pentavalent impurities or pentavalent materials, there are 5 single valence electrons at the outermost shell. So we have p-type semiconductor and n-type semiconductor, and when we connect a p-type semiconductor or with n-type semiconductor, there creates a p-n junction. So this connection can be made, and the common method is alloying. By the process of alloying, we connect a p-type semiconductor and the n-type semiconductor, and there creates a junction. We call it p-n junction, and diode is nothing but a p-n junction. The definition of diode is a p-n junction device that maintains the unidirectional flow of current. It means diode lets the current flow in only one direction. So here is the symbolic representation of a diode. There is an arrowhead and a straight line. The left hand side of the arrowhead is called anode, and right hand side of the arrowhead is called cathode. In practical situation, when we hold a diode in our hands, there is a silver marked portion. That portion is cathode and the rest portion is anode. Also, the left hand side portion of the arrowhead is denoted as P type or P side of the diode, and right hand side of the arrowhead is denoted as N side or N type of the diode, and the straight line represents the depletion layer. There are some various types of biasing of diode. These are no biasing, forward biasing and reverse biasing. In case of no biasing, the diode is not connected to any external biasing source. In case of forward biasing, the P terminal of the diode is connected to the positive terminal of the battery, and N terminal is connected to the negative terminal of the battery. And in case of reverse bias condition, the P terminal of the diode is connected to the negative terminal of the battery, and N terminal of the diode is connected to the positive terminal of the battery. Now we will be seeing various aspects of p-n junction diode. We have said that diode is nothing but a p-n junction, and we have seen the biasing. Biasing is the application of external voltage source across the p-n junction, and we have seen 3 types of biasing. Now we will be discussing about the p-n junction. In p-n junction, a p-type semiconductor is connected to an n-type semiconductor. In p-type semiconductor, we dope the semiconductor with trivalent impurities. These impurities or materials have one less electrons to fill its octet in the outermost shell, and they always try to accept one electron. So this type of materials are acceptor materials. In case of pentavalent impurities, they have an extra valence single electron which they try or tend to donate. So this type of atoms are called donor atoms. In case of p-type semiconductor, we know the majority charge carriers of p-type semiconductors are holes, and in n-type semiconductor the majority charge carriers are electrons. So in p-type semiconductor the concentration of holes are much, and in n-type semiconductor the concentration of electrons are much. So there sustains the potential gradients of holes from p side to n side. Also there sustains a potential gradient of electrons from n side to p side. So the hole stands or tries to get through the p-n junction and tries to recombine with the electrons, as well as the electron tries to go through the p-n junction and try to recombine with holes. And this is the case when we connect a p-type semiconductor with n-type semiconductor. At first we will be applying no bias, and we will be discussing no bias condition. So we have discussed that p-type semiconductor have acceptor ions and the majority charge carriers are holes, and n-type semiconductors have donor ions and majority charge carriers are electrons. And in p-type semiconductor the holes have mass concentration, and in n-type semiconductors electrons have mass concentration. So due to this concentration gradient, holes tries to recombine with electrons. Also the electrons tries to recombine with the holes, and as a result of this recombination the holes get recombined with the electrons and electrons get recombined with the holes. For this reason immobile ions will be surface out and this is because of diffusion, because due to higher concentration gradient of holes from p side, the holes will try or tend to pass through this p-n junction and get recombined with the electrons, and due to higher concentration of electron in n side, the electrons will tend to get recombined with holes on the other side. So for this diffusion the immobile ions will surface out. It means there will create a layer of negatively charged ion on p side and a layer of positively charged ion on n side, and there no mobile charges will exist there, but only immobile charged ions or immobile ions will exist there in this region of depletion region. We call this region as depletion region. If we further discuss on this concept, at present the acceptor ions sustain with the holes in p side, and in the n side the donor ions sustain with the electrons. So the charge neutrality is maintained, but due to the excessive potential gradient from p side to n side of holes tries to get recombined with electrons. As a result, negative immobile ions get uncovered in p side, and due to high potential gradient of electrons from n side to p side, electron tends to get recombined with the holes, and positively charged immobile ions creates on the n side, and the layer of positively charged and negatively charged ion creates an electric field. This electric field acts as a barrier or hindrance of the further charge movement through this depletion region. As this electric field acts as a huge barrier of the flow of majority charge carriers, so this electric field or barrier is known as potential barrier. Due to this electric field, positively charged holes cannot pass through this p-n junction and get recombined with electrons, as well as electrons get hindered to get recombined with the holes, and this region is called the depletion region. This is the case of no bias condition, where there is no external bias is applied, and due to this diffusion of majority charge carriers, the majority charge carriers makes a flow of current. This current is known as diffusion current. And there is another type of current, which is a drift current. Now we will be seeing various types of the other two types of biasing conditions, which is forward biasing and reverse biasing condition. In case of forward bias condition, the p terminal of the semiconductor or p-type semiconductor is connected to the positive terminal of the battery, and n-type semiconductor is connected to the negative terminal of the battery. As a result, the positive potential will repel the holes in the p side, and negative potential will repel the electrons in the n side. This causes the holes to get further recombined with the negative immobile ions on the p side junction, and this also causes the electrons to get recombined with the positively charged immobile ions on the n side junction. As a result, the holes get recombined with negatively charged immobile ions on p side, and electrons get recombined with positively immobile charged ion on n side. As a result, the depletion region will get decreased. Also, the barrier potential get decreased. The barrier potential get decreased in the amount of barrier potential minus the external voltage amount. As a result, the barrier potential will also decrease. The depletion region will also get decreased. Now, if we further keep on increasing the forward bias potential, the depletion region will get decreased and keep on decreasing. The barrier potential will also keep on decreasing until or unless a sudden flood of electron passes through this junction, passes through this p-n junction. This causes a discrete flow of current, which is due to the majority charge carriers. So, by applying much more forward bias potential, we get a current due to the majority charge carriers, or due to the flow of majority charge carriers through the p-n junction, and this current is due to the majority charge carriers. Also, we know that in p-type and n-type, both type of semiconductors, there sustains a minority charge carrier. In n-type semiconductor, the minority charge carrier is holes, and in p-type semiconductor, the minority charge carriers are electrons. A small amount of current also flows through the p-n junction due to the minority charge carriers, and this current is known as the leakage current or reverse saturation current. And this leakage current or reverse saturation current always depend on the temperature. Now we have seen that how current flows through the majority charge carriers in forward bias conditions. If we summarize, when we keep on increasing the positive potential, external biasing potential in forward bias conditions, the depletion region keeps decreasing, the potential barrier also keeps decreasing, and the potential barrier become low and low, and one time we overcome the potential barrier and the flood of electron passes through the p-n junction. Thus, we get the current flow through the p-n junction due to majority charge carriers. Now we will be seeing what happens in the case of reverse bias condition. In case of reverse bias condition, the p terminal of the diode or p-n junction is connected to the negative terminal of the battery, and terminal of the p-n junction is connected to the positive terminal of the battery. As a result, these holes will be attracted and drawn towards the negative terminal of the battery from the P side, and from the N side the electrons will be attracted and drawn towards the positive terminal of the battery. So as a result, the depletion region width will get increased as these electrons will be drawn towards the positive terminal of the battery and holes will be drawn towards the negative terminal of the battery. There will be more uncovering of negative immobile ions in P side and more uncovering of positive immobile ions in N side. So as a result, the depletion region will get increased. As a result, the barrier potential will also increase. The barrier potential amount will increase by the amount of VD or external biasing source. So due to the high potential barrier or high depletion region width, no current flows through the PN junction due to the majority charge carrier, as this high potential barrier hinders the flow of majority charge carriers through the PN junction. But I have said that previously that there is a small amount of current that flows through the PN junction due to the minority charge carriers. In N type, the minority charge carriers are holes. In P type, the minority charge carriers are electrons. In case of reverse bias condition as well, the current, a small amount of current flows through the PN junction due to the minority charge carriers. And we call this current as a reverse saturation current or leakage current. This current only depends on the temperature. Now we have discussed no bias condition, forward bias condition and reverse bias condition. Now we will be seeing simply the IV characteristics of a PN junction diode. So for this we will draw a plot where x-axis represents the voltage across the diode and y-axis represents the current through the diode. At first we will be seeing the case of forward bias condition, and we will take in consideration for silicon whose potential barrier is 0.7 volt. So in forward bias condition, the P terminal of the diode is connected to the positive terminal of the battery, and terminal is connected to the negative terminal of the battery. And we know and current and voltage relationship of diode, here is ID is equal to IS e to the power Vd by eta Vt minus 1, where Is is the reverse saturation current, Vd is the voltage across the diode, and eta Vt is constant. From this equation we can see when we will be applying no bias or no external bias, when Vd is equal to 0, if we put Vd is equal to 0 in this equation, the ID current will be also 0. So the current will be 0 when Vd will be 0. We can also say that whenever we will be applying no external bias, unless or until we overcome or exceed the potential barrier, the diode or PN junction will not let the current to flow or will not let the majority charge carriers to flow through the PN junction. So if we keep on increasing the potential barrier in forward bias direction, unless or until we reach towards the potential barrier of silicon, we will not get any flow of current, because this potential barrier will hinder the flow of majority charge carriers through the PN junction, and we will not get any flow of current. Whenever our applied forward bias will be equal to potential barrier, which is 0.7 volt, the diode, the barrier potential will keep on decreasing. As we increase the forward bias potential, the barrier potential will keep on decreasing, the potential barrier will keep on decreasing, and the depletion region width will be keep on decreasing. Whenever we will reach the potential barrier, whenever our applied voltage will be equal to the potential barrier, we will see a small rise in current. We will see a small rise in current through the PN junction diode, and whenever we will exceed the potential barrier, whenever our applied external forward bias potential exceeds the barrier potential, a discrete flow of current flows through the PN junction, and we see a discrete or sudden flow of current in the graph. The current rises districtly because after exceeding or after overcoming the potential barrier, flood of electrons pass through the PN junction, and due to the majority charge carrier flow, a huge current, we see a huge rise in current through the PN junction. This is the case of forward bias condition, and now we will be seeing what is the case of reverse bias condition. In reverse bias condition, the P terminal of the diode is connected to the negative terminal of the biasing source, and N terminal of the diode is connected to the positive terminal of the biasing source. We have previously said that during the reverse bias condition as well, a small minority charge carrier flow causes a current which is known as reverse bias, reverse saturation current, or leakage current. Here is the small amount of reverse saturation current or leakage current which is due to the minority charge carriers that flows through the PN junction, and this minority charge carrier flow depends only on the temperature. So in case of reverse bias condition, initially we get a small amount of current in microampere range which is due to the minority charge carriers which flow through the PN junction. Now if we keep on increasing the reverse bias voltage, after a certain voltage, the current suddenly starts flowing districtly in reverse direction. We see a sudden rise in current, and the voltage after which the diode current starts increasing districtly in reverse direction. This voltage is called as breakdown voltage or Zener voltage. The voltage after which we see a district rise in current or sudden flow of current in reverse direction, and current starts flowing or current enters in the breakdown region. This voltage is called as breakdown voltage, and the region here is denoted as breakdown region. And in this breakdown region, for this huge flow of current in reverse direction, normal diodes get burned out, but Zener diodes conduct well in this region. So this is the case of reverse bias condition. There is another term called peak inverse voltage. Peak inverse voltage is the maximum reverse bias voltage. Maximum reverse bias voltage in this region, after which the current starts to flow districtly in reverse direction or enters into the breakdown region. Peak inverse voltage denotes this maximum reverse bias voltage, after which the diode current enters into the breakdown region and starts flowing districtly in the reverse direction. So this is simply the explanation of PI characteristics of PN junction, as well as I have discussed the PN junction diode, the biasing of diode, no bias condition, forward bias condition, and reverse bias condition, and at last I have discussed the VI characteristics of PN junction diode. This was all about my topic of discussion. Thank you.